Come on, my dears, last time by mistake the illustration number 4 was left out. So, let us cover it up first and then we will proceed further in the theoretical part. Please kindly read this statement of illustration number 4. Come on, read it. Look, what is the formula for finding torque exerted on a single particle? You must have remembered from the last lecture, vector tau equals to vector r cross vector f. And remembered we had studied formula of vector product in the form of determinant in semester number 1. Come on, vector a cross vector b means 3 by 3 determinant, I hat, j hat, k hat, ax, ay, az, bx, by, bz. Likewise, here 3 by 3 determinant, come on, I hat, j hat, k hat. Then we should write 3 components of first vector. First vector is position vector. Its 3 components are given to you in the statement and they are 4, 6, 12. Similarly, in the third row, we are supposed to write 3 mutually perpendicular components of this second vector, which is right now force vector, for which 3 mutually perpendicular components are given to you. Come on, 6, 8, 10. Now simplify. How to expand this 3 by 3 determinant? You know very well. First of all, we have to take this member, that is I hat, and with that, which determinant will be in multiplication? 2 by 2 determinant, 6, 12, 8, 10. And how to simplify that? Come on, this into this minus this into this, correct? So, 10 into 6, that is 60, minus 12 into 8, that is 96, correct? And here we write minus j hat, and with that just cancel this column, cancel this row. What is left out? 4, 12, 6, 10. How to take the multiplication? You know, 10 into 4 minus 12 into 6. This into this minus this into this. 10 into 4, that is 40, minus 12 into 6, that is 72. And with a plus k hat, discard this column, discard this row. With plus k hat, what will be in multiplication? 4 into 8, that is 32, minus, come on, 6 into 6, that is 36. And now simplify. Come on, 60 minus 96, it is minus 36 into I hat. 40 minus 72, it is minus 32, but minus minus plus 32 j hat. Come on, 32 minus 36, it is minus 4 into k hat, minus 4 into k hat. Simple. So, we have found out vector tau, but you know, in case of rotational motion of a rigid body performed about stationary axis of rotation, what is the component of torque which is really responsible for producing torque, for producing rotational motion? What is the component of torque which is responsible for producing rotational motion? You know that component which we studied last time in the theoretical part. What was that component? Vector tau dot n hat. Vector tau dot n hat is the required component. At present, we are looking for this component which is responsible for producing rotational motion. Come on, vector tau, and come on, its 3 components you can write now. This is x component minus 36, y component 32, minus 4 is the z component, dot. Come on, this is n hat, which is unit vector chosen along axis of rotation, and that unit vector you are given in the statement 1 upon root 3 into 1, 1, 1. Now this part as it is, dot, just multiply inside. So 1 upon root 3, comma, 1 upon root 3, comma, 1 upon root 3, fine. And now take the dot product. You know how to take the dot product? Come on, If it is vector A dot vector B, what is the formula for finding dot product in terms of components? Ax bx plus ay by plus az bz, like that. Here also, this into this plus this into this plus this into this. Just take it one by one. This into this will give you minus 36 upon root 3 plus this into this, that is 32 upon root 3 plus this into this, but here it is minus, so minus 4 upon root 3, minus 4 upon root 3. Now root 3, root 3, root 3, so in LCM it will be root 3, and you know minus 36 minus 4, that is minus 40. Minus 40 plus 32 will give you minus 8. Now just take modulus on both the sides. So when you take mod here, here also you can take modulus, and when you take modulus, from minus it will become plus 8 upon root 3. What are you finding? You are finding component of torque. It will have same unit as that of torque. What is the SI unit of torque? Newton into meter. Newton into meter. Correct? Right now, the coordinates, components of position vector are given to you in meter, and components of force vector are given to you in Newton. That's why the unit of torque is Newton into meter. If the components of position vector are given to you in centimeter, and the components of force vector are given to you in dyne, then you may write here dyne into centimeter, dyne into centimeter. Right now in SI unit, come on, Newton into meter. Got it? Now we proceed further in the theoretical part. What is the article? See the title. Angular momentum of a single particle. The way any particle performing linear motion possesses linear momentum, similarly, a particle performing angular motion possesses angular momentum. So far a single particle is concerned, its symbol is vector small l. Vector small l gives you angular momentum of a single particle. How is it defined? I am showing you. It is defined through this vector relationship. What is that vector product? Come on, vector r cross vector p. Vector L equals to vector r cross vector p. Don't get confused. If it is vector r cross vector f, then it is vector tau, and here it is vector r cross vector p. It is vector L. Okay, fine. Now using this, you can define what is called angular momentum of a single particle. Very simple. Definition is very simple. Just look at here. If vector r is the position vector of a given particle with respect to a given reference point, and if vector p is its linear momentum, then a vector product, which vector product? Vector r cross vector p is called its angular momentum with respect to that reference point. I repeat, if vector r is the position vector of a given particle with respect to a given reference point, and if vector p is its linear momentum, then a vector product, vector r cross vector p, is called angular momentum of that particle with respect to that reference point, shown by symbol vector small l. Fine. Now consider this figure. As usual, we have shown this right hand side axis as x axis, vertically upward axis as y axis, and perpendicular to the plane of the figure and coming outward, that is z axis, which is perpendicular to x as well as y axis. So z axis is like this. And now think of xz plane. This is x axis, this is z axis. Think of xz plane means plane passing through x and z axis, it is this plane. Correct? Fine. Now in this plane, you just consider a single particle, say particle q. Say particle q. Correct? What is capital Q? It is a considered particle. Fine. Now at present we are considering that particle in this xz plane, and when it is lying over here, its position vector with respect to origin is vector small r. Right now we take origin as our reference point, Suppose this particle moves in this direction. In whichever direction the particle is moving, in the same direction it will have its linear velocity. And you know vector p equals to m into vector v. It shows that directions of vector p and vector v are same. So in the same direction the particle will have its linear momentum also. Fine. Now this is direction of vector r, correct? This is direction of vector p. This is direction of vector r. This is direction of vector p. What is this then? Angle between them, let it be theta. Fine. And now tell me, under these circumstances, what is called angular momentum of this particle with respect to this reference point? Just now all of you have defined, it is vector L equals to vector r cross vector p. Let me repeat it last time now. If vector r is the position vector of a given particle with respect to a given reference point, and if vector p is its linear momentum, then a vector product vector r cross vector p is called angular momentum of that particle with respect to that reference point. Fine. Now find out direction of this. How would you find out direction of this vector product? First of all, you have to place both the vectors on each other such that they have a common tail. And for that purpose, what I do, I just shift this vector p from here to here. Correct? Come on. Just shift it from here to here. This is vector r, this is vector p. Come on, vector r, vector p. They both have their common tail over here. And now you can find out vector r cross vector p the way I am showing you. Come on. Take this as vector r. Come on. Take this as vector r. Correct? Take this as vector p. This is with the pink color. This vector is vector r. This is with the blue color, vector p. Vector r, vector p. Vector r, vector p. And now think of a plane passing through these two vectors. Plane passing through these two vectors. Correct? Now imagine a right-handed screw which is perpendicular to this plane. That screw is suppose this. Correct? This way. And now you are supposed to rotate this screw in a manner first vector rotates towards second vector. In this order, first vector is vector r, second vector is vector p. So I should rotate vector r towards vector p. Vector r is this, vector p is this. I should rotate first vector towards second vector through the smaller angle between them. Then I should rotate it this way, this way, this way. And in the same manner, I should rotate this right-handed screw. Correct? If I rotate this right-handed screw in this manner, correct? If I rotate it this way, it will advance vertically upwards, That is why you can see direction of vector r cross vector p and hence direction of vector L. At present, I have shown vertically upwards. That is along positive y-axis. It is vector L, which is vector r cross vector p. And don't you know, direction of a vector product is always perpendicular to both the given vectors. Look, this is vector r, this is vector p, and if this is vector L suppose, then tell me, how to find this vector? This vector is perpendicular to this also, the same vector is perpendicular to this also. Angle between these two is 90 degree, correct? Angle between these two is also 90 degree. So this is such a vector which is perpendicular to r also, perpendicular to p also, and the same thing I have shown by perfect right angles in the diagram. You can see this is perpendicular to vector r. You can see this right angle, correct? It is perpendicular to vector r. This is also perpendicular to vector p. You can see this right angle, correct? Now this is parallel to this. This is parallel to this, correct? Similarly, this is parallel to this and this is parallel to this, correct? That is how you will show these right angles perfectly, okay? Fine. Take magnitudes on both the sides, come on. When you take magnitude here, it is modulus of vector L. When you take magnitude here, modulus of vector r cross vector p. Come on, modulus of vector L, what is it? L. And if it is vector a cross vector b, what is the modulus? A b sin theta. Similarly, here r p sin theta. Fine. Now find out SI unit. Come on, SI unit of angular momentum, you can write all these quantities SI units. Come on, distance, for distance, come on, meter. For momentum means mass into velocity, unit of mass is kilogram. For velocity, you know it is meter per second. Whether it is sin theta or cos theta or tan theta, in short, any trigonometric function is there, it has only numerical value, has no unit. Fine. Now simplify. Kilogram as it is, meter into meter, meter square upon second, meter square upon second. And now this SI unit is as good as joule into second, joule into second. Had it been linear momentum, then Newton into second. Right now it is angular momentum, then unit is joule into second. Okay. So either you say kilogram into meter square upon second, or you say joule into second, one and same. When L will be equal to 0, when L will be equal to 0, I am showing you. First, when R is 0, naturally L will be 0. Second, when P is 0, naturally L will be 0. If sin theta is 0, then also L will be 0. When sin theta is 0, then also L will be 0. But tell me, when sin theta will be 0, provided theta is 0 degree or 180 degree. Now tell me, when theta will be 0 degree or 180 degree, I am showing you. Instead of taking reference point here, you just take reference point here on the line of action of this linear momentum. On this line, which contains the direction of linear momentum, you just consider reference point over here. If you take reference point here, then with respect to this reference point, position vector of this particle will be like this, correct? And now this is vector r, in the same direction there is vector p. So vector r, vector p, vector r, vector p, they will be in the same direction. And angle between two vectors in the same direction would be 0 degree, would be 0 degree. That's why I am putting theta equals to 0 degree. And if you take reference point over here, suppose, then with respect to this reference point, what is the position vector of this particle? It would be this way, correct? Opposite to vector p, opposite to vector p. So if vector r and vector p are opposite, then angle between them will be 180 degree. In short, if we take reference point on the line passing through the vector p, then theta is either 0 or 180 degree. In both the cases, come on, sin theta would be 0. And when sin theta is 0, come on, L will be 0. Correct? Remember 4 points. First, it is not necessary that this particle must be of a rigid body. Not necessary. It is not necessary to take that particle every time in the horizontal plane. Not necessary. It is not necessary that direction of linear momentum must be in the horizontal plane, not necessary. And it is not necessary to take every time origin as a reference point, not necessary. I repeat, particle need not be of a rigid body. Particle may not be in the horizontal plane. Particle may not have linear momentum in the horizontal plane. And origin may not be taken as a reference point. Okay, fine. Now, mention of a reference point is a must while defining angular momentum, because if you keep other factors as it is and if you simply change this reference point, then with respect to new reference point, the distance of this particle would change and theta also may change. So either r or theta or both of them are changing, naturally L value will change. So whenever you say that angular momentum of a particular particle is this much, you must say with respect to which reference point, because the moment you change the reference point, either r or theta or both of them will change, ultimately it will change the value of angular momentum. So while mentioning angular momentum, mention of a reference point is a must, is compulsory. Now let us go for one very small proof. Prove that angular momentum is equal to moment of linear momentum. Angular momentum is equal to moment of linear momentum. How to prove it? Very simple. Start with the basic definition. Come on, from the basic definition we know the magnitude formula. L equals to Rp sin theta. L equals to Rp sin theta. Fine. Can you rewrite? P P into r sin theta. Come on, P into r sin theta. What is P? P is linear momentum. What is r sin theta? I am showing you. If this angle is theta, this also will be theta because vertically opposite angles are always equal. And now draw one perpendicular from this reference point on this line passing through vector P. When you draw perpendicular, the foot of perpendicular is point M and distance OM will give you perpendicular distance of reference point from this line passing through vector P. Fine. Now that perpendicular distance, if you want, it is nothing but component of r opposite to theta. Component of r opposite to theta, what is it? R sin theta. So this perpendicular distance OM is nothing but r sin theta. So this r sin theta is perpendicular distance. Perpendicular distance. Okay. And I told you last time, product of a vector physical quantity and perpendicular distance of line of action of that physical quantity from some reference point. Such a product is going to give you moment of that vector physical quantity. Right now that vector physical quantity is linear momentum. So such a product would give me moment of linear momentum. Moment of linear momentum. Moment of linear momentum. So angular momentum is nothing but moment of linear momentum. That is what we have proved. Now let's go for finding components of angular momentum. Very simple. You know from basic definition, vector L equals to vector r cross vector P. Vector L equals to vector r cross vector P. Don't you know vector A cross vector B formula in terms of components? Just now we had seen 3 by 3 determinant, I hat, J hat, K hat, AX, AY, AZ, BX, BY, BZ. Similarly here, 3 by 3 determinant, come on, I hat, J hat, K hat, 3 components of vector R. They are X, Y, Z. 3 components of vector P, come on, Px, Py, Pz, fine. And now expand this, you know how to expand it? With I hat, what will be in multiplication? This into this minus this into this. Come on, speak out. With I hat, y into Pz minus z into Py. Y into Pz minus z into Py. And with that, in multiplication, you should write I hat plus j hat, I am writing. I am not writing minus z, I am writing plus z. If you write plus j hat, then you should take this into this minus this into this. When you take this into this, it is z into px. Here it is z into px. Minus this into this, that is x into pz. X into pz. And that into j hat plus with k hat. What is in multiplication? Come on, this into this minus this into this. So it is x into py minus y into px. X into py minus y into px. That into k hat. Fine. And now you know the representation of a vector in 3 dimensions which you have studied in semester 1. What was vector capital A? It was AXI hat plus AYJ hat plus AZK hat. Similarly, vector L is how much? LXI hat plus LYJ hat plus LZK hat. Here it is. Vector L equals to LXI hat plus LYJ hat plus LZK hat. Wait. Compare these two. When you compare, come on, what is the coefficient of I hat? Lx. And here coefficient of I hat is this much. How much? Ypz minus Zpy. So if you compare, then Lx formula would be Ypz minus Zpy. Lx formula would be Ypz minus Zpy. Similarly, compare the coefficients of J hat. Here it is Ly and here it is Zpx minus Xpz. Come on, Ly equals to Zpx minus Xpz. Come on, compare the coefficients of K hat. It is Lz equals to Xpy minus Ypx. Lz equals to Xpy minus Ypx. Got it? And this is how you can find out all the 3 mutually perpendicular components of vector L, which are normally called Cartesian components of angular momentum. Cartesian components of angular momentum. Fine. Now we are going to prove one very important result, and that result is this: vector tau equals to vector dl by dt. From this, if you want to obtain unit of angular momentum, you can directly read from here. unit of torque if you write joule, and then unit of time will be in there in multiplication, which is second. So, unit of angular momentum would be torque into time, unit of torque into time, unit of torque if you take joule, then into second. Joule into second is the unit of angular momentum from here. Now, let us prove this result. Vector tau equals to vector dl by dt, that is what we have to prove. Start with the basic definition. We know vector L equals to vector r cross vector p. Here it is. Vector L equals to vector r cross vector p. Vector L equals to vector r cross vector p. Just take d by dt on both the sides. D by dt on both the sides. Fine. When you take d by dt here, it is vector dl by dt. And when you take d by dt here, it is d by dt of vector r cross vector p. Fine. And now tell me, vector dl by dt as it is. Come on, last time I told you specific rule for taking derivative of a vector product. What was that rule? First vector cross derivative of second vector plus derivative of first vector cross second vector. I repeat, first vector cross derivative of second vector plus derivative of first vector cross second vector. So, here it is vector r cross vector dp by dt plus vector dr by dt cross vector p. Fine. Now, this part as it is, vector r as it is. Don't you know Newton's second law? What is the mathematical form? Vector f equals to vector dp by dt. Vector f equals to vector dp by dt. Speak reverse. Vector dp by dt can be replaced by vector f. Vector dp by dt can be replaced by vector f. And now tell me, time rate of change of position vector is going to give you instantaneous linear velocity shown by symbol vector v. So, vector dr by dt is nothing but vector v cross vector p as it is. And now tell me, last time we had defined what is called vector r cross vector f. It is nothing but torque vector, vector tau. And just let me find out magnitude of this part. If I want magnitude of vector v cross vector p, then magnitude of vector a cross vector b, how much it is? A b sin theta. Similarly, magnitude of first vector multiplied by magnitude of second vector multiplied by sine value of angle between them. But here you can see, whatever is the direction of velocity, same is the direction of momentum. I mean to say these two vectors point in the same direction. And if two vectors point in the same direction, then angle between them is 0 degree and sine 0 is 0. 0 into this would be 0. Any vector whose magnitude is 0 is called 0 vector. Is called 0 vector. So, vector v cross vector p, you must write 0 vector. Come on, put these two values here. Vector r cross vector f is nothing but vector tau. So, replace this by vector tau. Plus vector v cross vector p is nothing but 0 vector. Replace this by 0 vector. And when you add 0 vector with any other vector, it makes no difference, giving you vector tau. So, ultimately what we have proved, vector tau equals to vector dl by dt. Here it is. Vector tau equals to vector dl by dt. Vector tau equals to vector dl by dt. This is very important relationship between angular momentum and torque. And don't you find this equation very much similar or analogous to Newton's second law, vector f equals to vector dp by dt. How? Where it appears here force, there here it appears torque, meaning thereby torque is similar or analogous to force. Where it appears here linear momentum, there it appears here angular momentum, meaning thereby angular momentum is similar or analogous to linear momentum. And this whole equation is analogous to this equation, which represents Newton's second law. How would you give statement from this result? Time rate of change of angular momentum of a single particle is always equal to resultant torque acting on it, and direction of change in angular momentum of that particle is always in the direction of resultant torque. This statement is very much similar to Newton's second law of motion for linear motion. Correct? I repeat. Time rate of change of angular momentum of a single particle is always equal to resultant torque acting on it, and the direction of change in angular momentum is in the direction of resultant torque. Full stop. This very statement gives you a statement which is similar to Newton's second law. Okay, fine. Mr. Newton had never given any law for rotational motion, he had given laws of linear motion, correct? Fine. Now we go for finding total angular momentum of a system of particles. Total angular momentum of a system of particles. Look, see, when you are talking about a system of particles, say there are n particles, and with respect to a given reference point, the angular momentum of first particle I am taking by symbol vector small l1. Similarly, for second particle, let it be vector small l2. For the last particle, let it be vector small ln. And now just make their vector addition. It would give you total angular momentum of whole system shown by symbol vector capital L. Vector addition of angular momenta of all the constituent particles of a given system with respect to a given reference point is called total angular momentum of that whole system with respect to that reference point. I repeat, the vector addition of angular momenta of all the constituent particles of a given system with respect to a given reference point is called total angular momentum of that whole system with respect to that reference point. Fine. Now take d by dt on both the sides in each term on right hand side. Come on. Take d by dt here. So it will give you vector dl by dt. Vector dl by dt. Take d by dt here in each term. Come on, take it here. Vector dl1 by dt plus here vector dl2 by dt plus dash 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 plus here vector dln by dt. Tell me, what is vector dl by dt? What is vector dl by dt? Just now we have proved it is nothing but vector tau. So if you are talking about time rate of change of angular momentum of first particle, it will definitely give you torque exerted on first particle. Let it be shown by symbol vector tau 1. Similarly, this gives you vector tau 2 and this gives you vector tau n. And now tell me, last time we had defined vector addition of torques exerted on all the constituent particles of a given system with respect to a given reference point is called resultant external torque exerted on that whole system with respect to that reference point shown by symbol vector tau. So this is resultant external torque exerted on the whole system because resultant internal torque is 0. Because resultant internal torque is 0, this is nothing but resultant external torque. And that has come out to be equal to vector dl by dt. Just write reverse. Come on, vector tau equals to vector dl by dt. But which L? Here capital L. And remember in first chapter, come on, we had obtained this equation. Vector F equals to vector dp by dt. Which P it was? Capital P, total linear momentum of a system. Which L here? Capital L, total angular momentum of a system. This was resultant external force. This is resultant external torque. Correct? Would you like to give statement from this result in words? Very simple. The time rate of change of total angular momentum of a given system is giving you time rate of change of total angular momentum of a given system is equal to resultant external torque acting on it, and direction of change in total angular momentum is in the direction of resultant external torque. This statement is similar to Newton's second law for whole system. I repeat, time rate of change of angular momentum of a whole system is equal to resultant external torque acting on it, and the direction of change in total angular momentum is in the direction of resultant external torque. This statement is similar to Newton's second law for whole system. Okay, fine. Now we go for total angular momentum of a rigid body. Total angular momentum of a rigid body. My dears, what is rigid body? It is also a system of particles. And if you are talking about a system of particles, then don't you know total angular momentum can be found out using this vector relation. Come on, vector capital L equals to vector small l1 plus vector small l2 plus dash 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 plus vector small ln. Wait. Now we are talking about that rigid body which is performing rotational motion about stationary axis of rotation. You know what do we find? whenever any rigid body is performing rotational motion about stationary axis of rotation, say this way, then the directions of angular moment of all the constituent particles are found to be vertically upwards, means in the same direction. If all these vectors have same direction, you can add them like scalars. Not necessary that body should rotate this way. Suppose body is rotating this way. If body is rotating this way, then directions of angular moment of all the constituent particles come to be in vertically downwards. If all these vectors are vertically downwards, means in the same direction, again because they are in the same direction, you can add them like scalars. I mean to say, for rotational motion of a rigid body about stationary axis of rotation, directions of all these angular momentum vectors are in the same direction, and that's why you can add them like scalar. And then you should delete this vector sign and you should write simple scalar addition. L equals to L1 plus L2 plus dash 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 plus Ln. Look here, L equals to L1 plus L2 plus dash 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 plus Ln. But what is L equals to? L equals to Rp sin theta. Come on, L equals to Rp sin theta. L equals to Rp sin theta. Here theta is 90 degree, so Rp sin 90 degree. Look here. L equals to Rp sin theta. Theta is 90 degree, sin 90 is 1, so it is simply R into P. But you may have a question, why theta is 90 degree? Simple. Whenever any rigid body is performing rotational motion about stationary axis of rotation, direction of vector R for a given particle is parallel to plane of rotation. Not only that, with respect to center of the circular path, it is in the direction of radius. And you know vector P is always in the direction of vector V, and vector V is always along tangent. And for a circle, don't you know, radius and tangent are mutually perpendicular. So this is along radius, this is along tangent, they are mutually perpendicular, so angle between them is 90 degree. Just put it here. Rp sin theta, theta is 90, sin 90 is 1, so it is R into P. So wherever it is L, you can write R into P, but when you are talking about first particle, you should write here L1. And then here R1 into P1. That's why L1 equals to R1 P1. L1 equals to R1 P1. Similarly, L2 will be equal to R2 P2. L2 will be equal to R2 P2. What about Ln? It will be Rn into Pn. Ln equals to Rn into Pn. Right? Fine. R1 as it is. What is P? P equals to M into V. P equals to M into V. For first particle, P1 equals to M1 V1. P2 equals to M2 V2, for the last particle Pn equals to Mn Vn. But don't you know, V equals to R omega, V equals to R omega, just put the values here. V1 will be, come on, R1 omega, V2 equals to R2 omega, Vn equals to Rn omega. You might be having one question, why not omega 1, omega 2, omega n? Why I am putting everywhere only omega? Because whenever any rigid body is performing rotational motion about stationary axis of rotation, at any point of time, the values of angular velocity for all the constituent particles are same. And because angular velocities of all the constituent particles are same, you need not to show them by different symbols. You may show by same symbol, here also omega, here also omega, here also omega, because omega is at present constant. Okay. At any given point of time, the magnitudes of angular velocity for all the constituent particles are same, and that's why everywhere angular velocity is shown by symbol only omega. Don't write here omega 1, omega 2, omega n. Everywhere you write simply omega. So V1 is R1 into omega, V2 is R2 into omega, Vn is Rn into omega. Now simplify. M1 as it is, R1 into R1, that is R1 square. Come on. M2 as it is, R2 into R2, R2 square. Mn as it is, Rn into Rn, Rn square. Omega, omega, omega taken out, Omega is taken common, correct? And now, if you don't want to write such a long summation, you may just adopt a very easy symbol, say capital I. This omega as it is. So, what is the formula of total angular momentum of a rigid body? What is the formula? L equals to I omega. L equals to I omega. Tell me, in place of which bracket you have substituted here capital I? Capital I here is substituted for this bracket. Which bracket? M1 R1 square plus M2 R2 square plus dash 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 plus Mn Rn square. Wait, this bracketed part which is at present shown by symbol capital I. In physics, we have given specific name to that quantity. It is called moment of inertia. Moment of inertia. Moment of inertia of what? Of a rigid body. About what? About given stationary axis of rotation. It is called moment of inertia of a given rigid body performing rotational motion about given stationary axis of rotation. Fine. Now, if you don't want to write this long summation, you want to write by single term, you may write it this way. What are we taking here? We are taking addition of which sort of terms? We are taking addition of the terms in which there is a product of mass and square of perpendicular distance of a given particle from stationary axis of rotation. Wait, mass into perpendicular distance square, mass into perpendicular distance square. Say for ith particle, mass is mi and perpendicular distance from axis of rotation is ri, it's a square. And because we are making addition of such terms, I must write sigma, and here this suffix I indicates order of particle. In order to include all the particles, this order should be changed right from minimum to maximum, from first to last, That's why I am putting I equal to 1 to n. Got it? Sigma, come on, from I equal to 1 to n of mi ri square. Okay. Now tell me, in case of rotational motion about stationary axis of rotation, we find that these two are vectors. Not only that, they are in the same direction. If the rotation is this way, then vector omega and vector L, both of them come out to be vertically upwards. If rotation is this way, both the vectors come out to be vertically downwards. I mean to say, for a rotational motion of a rigid body about stationary axis of rotation, these two vectors have same direction. If these two vectors have same direction, then taking I as a scalar, you may write this scalar relationship in a vector form this way. Vector L equals to I into vector omega. I as it is, and because these two are vectors having same direction, you may write vector L equals to I into vector omega. This gives you total angular momentum of a given rigid body. What is the formula? Speak out. Vector L equals to I into vector omega. Correct? And don't you find this formula very much similar to this formula? Vector P equals to M into vector V. Vector P equals to M into vector V. What is this? Linear momentum. What is this? Angular momentum. There is a similarity. Come on, what is this? Linear velocity. What is this? Angular velocity. There is a similarity. Now, looking to the analogy or similarity between these two equations, can't you say that moment of inertia must be similar to mass in linear motion? Come on. Moment of inertia is that physical quantity in rotational motion which is similar to mass in linear motion. Correct? Sometimes we call moment of inertia as mass of rotational motion. Mass of rotational motion. Actually, it is not simply mass. It is mass into square of perpendicular distance. Okay? Its SI unit would be kilogram into meter square. Kilogram into meter square. So, it is not simply mass. Okay? Fine. Now, just take d by dt in this equation on both the sides. When you take d by dt here, it is come on d by dt of vector L, and when you take d by dt here, d by dt of I into vector omega. But what is this? Vector dl by dt. Come on, vector dl by dt. Come on, when you take derivative of this product, and in that, for a given rigid body rotating about given stationary axis of rotation, it so happens that value of I is constant. And because value of I is constant, you can take it out of the symbol of this derivative, you may take it out. And then left is vector d omega by dt. Vector d omega by dt. Wait, what is vector dl by dt? What is vector dl by dt? Just now we have proved to be equal to vector tau. So this can be replaced by vector tau. Correct? I as it is, and last time we had studied time rate of change of angular velocity is going to give you angular acceleration shown by symbol vector alpha. Correct? What is the important relationship you got between angular acceleration and resultant torque? What is the formula? Vector tau equals to I into vector alpha. Vector tau equals to I into vector alpha. Don't you find this equation similar to this equation? Vector F equals to M into vector A. Vector F equals to M into vector A. Don't you know from first semester, resultant force equals to mass into acceleration. Correct? Only acceleration means linear acceleration. Only acceleration means linear acceleration. Got it? Now tell me, this is force, this is torque, there is a similarity, correct? This is linear acceleration, this is angular acceleration, there is a similarity. And hence, once again we can say that the similarity or analogy between moment of inertia and mass is established once again. Moment of inertia is that physical quantity in rotational motion which is similar to mass in linear motion, correct? Now we go for law of conservation of angular momentum. What do you mean by conservation? Keeping constant. Here we are talking about conservation of angular momentum. So angular momentum would remain constant. But under which circumstances, that is what I have to show you. Come on. Vector tau equals to vector dl by dt. Here it is. Vector tau equals to vector dl by dt. I am putting one condition. If a vector tau is 0, if this is 0, this also will be 0. Now tell me, derivative of which term would be 0? Derivative of a constant term would be 0. So when this part is 0, this vector L must be constant. Come on, vector L must be constant. Constant means what? Conserved. What is conserved here? Angular momentum. That's why when you join these two, you will get statement of law of conservation of angular momentum. How would you give the statement? Whenever resultant external torque exerted on any system is 0, then its total angular momentum would remain constant. This very statement is called law of conservation of angular momentum. I repeat. Whenever resultant external torque exerted on any system is 0, its total angular momentum remains constant. This statement is called law of conservation of angular momentum. Fine. Now, one definition we are taking. This is the point. Maybe asked in the examination. Look, vector tau equals to I into vector alpha. Then take magnitude. Tau will be equal to I alpha. Find out I, it will be tau upon alpha, tau upon alpha. To define this quantity, what we do normally, we take denominator 1 unit. So take alpha equal to 1 unit. When you take alpha equal to 1 unit, put it here, then I will be equal to tau. So moment of inertia is nothing but external torque required to produce rotational motion in a given rigid body about given stationary axis rotation with 1 unit angular acceleration. External torque required to produce rotational motion in a given rigid body about given stationary axis of rotation with 1 unit angular acceleration is called moment of inertia of that rigid body about that stationary axis of rotation.